Hi everybody, how you doing? Ready to learn some GIS? Did you have fun in lab yesterday? I think there were 8 plus 5, 13, 14, 15, 16 or 17 of you that came into lab yesterday. So there's more people in the class than came to lab yesterday. So I hope those of you who didn't come in the lab, I hope you're doing all right. But I think some of you find the experience of learning GIS, jumping in and learning it, a little disorienting, and that's to be expected. There's a learning curve associated with learning anything new, and here you're learning software and the way of thinking about GIS problems, or problems that can be solved using GIS at the same time. Once you start to build your skill set, you're going to be able to do amazing things. So, happy Friday, everybody. Today I want to do two main things. One thing I want to do is I want to introduce you to some concepts revolving around the idea of how do you know where you are on the surface of the earth, okay? So we're going to do that first, spend about 20-25 minutes doing that. And then we are going to go to ArcGIS Online and finish working through some of the examples that are in the textbook Understanding GIS. We might not do everything to the letter as it's laid out procedure-wise in the textbook. Instead, we'll do some other stuff. I'll show you some other features. So if you can, put a hello in the comments. I want to know that you're there and listening. Let's get started. If you have any questions, put them in the comments. All right. If there's something I'm doing and you want me to slow down or say it again, let me know. All right. So let's see where to begin. I think the place to begin, I made some animations and I posted these. These animations aren't made with ArcGIS Pro. They're made with JavaScript, so they run in a web browser. And all right, I like seeing these hellos in the comments. Hi Logan, hi Chris, hi Michelle, hi Sean, hi Cole, hi Brianna, hi Christina, hi Gracie, hi Frankie, hi Abby. Happy Friday, everybody. So I made these. Let's see if I can get this open. Oh. Okay. And what I'm going to do, let's see if I can go to it. I bookmarked it. Haha, look at that. So I made this animation in JavaScript using a JavaScript library called D3. And it's super cool. But what you're looking at here is I created this animation of the globe, of the Earth. And it's rotating. On top of this this globe, which is spherical, do you think the Earth itself is spherical? What do you think? Anybody have a comment on that? In this simulation, the Earth is spherical, and on top of the sphere is laid down this grid. It's called a graticule. And this grid is commonly referred to as a grid of latitude and longitude. But you've heard that before. So latitude are the lines that go east and west. And I always remember that. I remember this from elementary school when we were talking about latitude and longitude for the first time. And my teacher said latitude starts with lat, like a ladder. They're like the rungs on a ladder. And longitude are the lines that go north and south. And this way of laying out this grid on the Earth's surface is is referred to as a polar coordinate system. And what you're to imagine is that there's a line from the center of the Earth to the surface of the Earth, and that line has makes an angle relative to the equator, okay, north and south, and that angle goes from 0 degrees to 90 degrees north, or 0 degrees and 90 degrees south. The convention is oftentimes, if you're going south from the equator, that's negative angles of latitude, okay? And then this line could go 360 degrees around, or think of it this way, 180 degrees in one direction or 180 degrees in the other direction to define the lines of longitude. And the reference there, does anybody know what so the reference for the angular position we call latitude, degrees north or degrees south on the globe, is the equator. So the equator is 0 degrees latitude. We are around 37 degrees north latitude here in West Virginia, in this area of West Virginia. And we're around 75, 76, 77 degrees west longitude here in West Virginia. So let's see if anybody knows this. So if you know this, put this in the comments. The reference point for latitude is the equator. What's the reference point for longitude? Does anybody know that? I wish I could, let me go back to the Chrome here. I wish I could pause this. I didn't write that into my code. Greenwich, England. Michelle says Greenwich, England. And let's say approximately Greenwich, England. So right about here is an area referred to as a longitude called the prime meridian. So we call that 0 degrees longitude, and if you go west from there, that's actually by convention negative angles of longitude. Or we could say, right around here is about 77 degrees west longitude, or minus 77 degrees longitude. If you go the other way, east, it's positive degrees longitude. So did anyone answer my question I had earlier? My question was, is the Earth actually a sphere? Is the Earth spherical? So if you think you know, leave a comment. All right. Next. What's next? No, not perfectly. That's right. So it's more, I like saying this word, it's more accurate to describe the Earth's surface as an ellipsoid. So it's actually, it bulges out more at the equator than at the poles. But many models of the way the Earth looks just assume the Earth is spherical, and it's not a bad approximation. But if you want accuracy, which you're usually after in GIS, using a spherical model of the Earth is not going to cut it. You use some sort of ellipsoid model of the Earth. I know what I want to say. So notice how, I wish I could rotate this. All the cool, it's flat. The Earth is flat. Could be. I've never been in space. I've just seen pictures. All of the lines of longitude converge at the poles. Okay, and the lines of latitude are equally spaced as you go up to the poles, but the longitudes converge at the poles, and that's important when we start talking about projections. All right, we're not quite there yet. All right, so let's see. Excuse me. What was the next thing I was going to say? So how do you, if you're using this sort of system, these polar coordinates, there's actually another parameter that you need to know, and that's latitude and longitude tell you where on the Earth's surface you are, and then there could be another parameter, elevation. And all of these things, if I say, I'm at 37 north latitude, 77 west longitude at an elevation of 400 feet, it begs the question, relative to what? And the answer to that depends. And so this is one of those mind-bending facts. But it shouldn't be that surprising if you think about it. The Earth it's not only an ellipsoid, it's very irregular. There's mountains, there's valleys, there's oceans, and it's not a flat surface. So that's a problem. And one of the problems associated with that is, yeah, although some of you are saying it's flat, it's not flat. But what we do is, when we make a map, is we're often, unless you're carrying around a globe, which isn't very practical, especially if you're trying to see large-scale features, in a lot of detail, you need to project something that's three-dimensional and somewhat spherical onto a flat surface. And that is impossible to do without introducing distortions. Okay? You can't do it. It would be like, imagine taking the peel of an orange and cutting it off and then flattening it. You couldn't do that without deforming the orange peel in a way that some parts stretch and some parts compress and some parts will be torn. And that the way that you would then, this is called projecting. So you're taking something that's three-dimensional and you're projecting it onto a two-dimensional surface. And the reason it's called projecting is because you can conceptualize this as if it were like, if I take this light and turn it on, it's going to be really bright, and shine it on my hand, I can project a shadow of my hand onto the roof or any other surface. And you can think about doing that with the Earth. You put a light source in the middle of the Earth and you shine the light through the surface of the Earth, and it projects the features of the Earth's surface onto a screen that surrounds the Earth. Depending on the kind of screen that you use, you get a very different map with different distortions. Okay, so I'm going to show you some examples of this. But what you should know is that, write this down. I wonder if I can do this up quick. We'll take a few notes. I'm trying here. All right, here we go. All right. So I got my digital whiteboard here. Is the normal? Sean says, is the normal map the Mercator projection? So the Mercator projection is very common, and we'll look at that in a little bit more detail. And we say the normal map, I think what you're referring to is like web maps, like on Google Maps. And Google Maps does use a version of the Mercator projection to create maps. And we're going to take a look at that. And I have an animation. I think when you look at the animation, you can understand the distortions that it introduces a little more. All right, so what we're talking about here is called, take that, let's use something thick. We're talking about a geographic coordinate system. Sorry, I'm writing a little messy. My pen is wonky. But it costs $100 to replace. Or GCS for short. And so a geographic coordinate system is defined by, it allows you to say where you are on the surface of the Earth in terms of latitude, longitude, and sometimes, or usually, elevation. Put that in little brackets there. And this is always going to be relative to some reference of, there's got to be some 0 point, 0 latitude, 0 longitude, 0 elevation. And this reference system is referred to as a datum. And write that down here. So a datum is a reference. And it includes a model of the Earth, which I said is called an ellipsoid. Sorry if I spell things wrong. I'm not a good speller. Ellipsoid. And then there's also horizontal. So that would be Greenwich, the prime meridian, and the equator, reference points. And then there's also a vertical reference. And the interesting about, so there are lots of different geographic coordinate systems, and if you know your position in one geographic coordinate system and you know your position in another geographic coordinate system, they don't agree. They could be off by a significant amount. So what's the best geographic coordinate system to use? My answer to that is the one we're going to use in this class predominantly, although we may encounter some others, is referred to as the World Geodetic System, or WGS, 1984. Okay, so this is a system that was created. So WGS 84 stands for World Geodetic System 1984, because 1984 was when it was created. And this is a standard that's curated by the National Geospatial Intelligence Agency. The reason, does anybody know why I say this model of the Earth, this system of geographic coordinate systems, is the one that I think is the most important? Does anybody know the answer to that? World Geodetic System, 1984. Well, no one say anything. So the reason that this one is probably the most important GCS in the world is because this is the system that's used by the GPS satellite system. Okay. So the global positioning satellite system. And so what that means is that if you're making a map and your map is saying, you're right here at this latitude and longitude, and that map uses WGS 84, that's the same position that your GPS unit would report to you. Okay, so there'd be consistency there. All right, that's a really important point for you guys to remember. When you get your latitude and longitude and from a GPS unit, it's telling you those numbers using this standard, WGS 84. Okay, that's really important for you guys to remember. All right, elevation is a little bit more dicey because depending on the GPS unit you're using, it may report your elevation relative to the ellipsoid, this bulging spherical-like thing that is the model of the Earth, or it might tell you your elevation based on a more complicated model of the Earth called EGM. What does that stand for? Earth Gravitational Model, which is a more irregular shape that takes into account the irregular lumpiness of the Earth in terms of its mass. And it's basically, so it does make a difference. If you're consistent using one system, you know, your elevation is really about how it changes from one place to another. And that's usually where all the interesting stuff is. But it could be quite different. You know, if I measure my elevation using these two different models here where I live, the difference is like 100 feet of elevation. All right. So, okay. So let's talk more about this this problem of taking a three-dimensional surface, a three-dimensional object, and projecting it onto a two-dimensional surface. And for the moment, it's like, you know, there's another thing here as well. You're scaling, right? You're taking something that's really big and you're making it smaller. All right. So let's take a look at some possibilities here. And I have a slide here to show you, okay, which summarizes the three main types of projections. Okay. So this right here, actually what we're looking at here, and I know it's rotating, but if you freeze this, what you're looking at is a projection onto a planar surface. It would be like, you know, if this little black box represents a movie screen, and you had a light source down here below this Earth, and you shine light up on top of this globe, and it would create a shadow, an image of the Earth on this flat surface, this planar surface. And not only is it a planar surface, but it's here. This is fun to say too. There's so many fun words in GIS. Orthogonal. Orthogonal means that it only touches the Earth at one point, and it's otherwise perpendicular to perpendicular lines going down to the surface would represent where that point on the surface would actually show up on the map. And so one type of projection is called a planar projection, taking this round ellipsoid Earth and projecting it onto a flat surface. Another type of, let's skip the one in the middle here. Let's look at this one. Another type of projection is called cylindrical. And this is like, you know, imagine surrounding the Earth with a movie screen that is actually a cylinder, and you have a light source in the middle of the Earth. You turn it on, light shines through the Earth and projects an image of the Earth's surface onto this cylindrical screen, and then you know, like the label of a can, you cut it and unfurl it so it's flat. Okay, so the Mercator projection is this kind of projection, the Mercator projection, which Sean has heard about before. The type of projection that you see on Google Maps is this type of projection. All right. And then the third category, main category, is called conical. And that's like you get a piece of paper and you make it into a cone like this and put it on the Earth's surface and then project light onto the surface, and then you have an image of the Earth, and then you cut the cone at one point and then unroll it, you get something like this. Okay, so most maps that you would see like in an elementary school classroom of the 50 United States um, are maps that are coming from this type of projection. There's a projection called the Albers Equal Area Conic Projection, and a lot of maps that you see in classrooms are this type of projection. Um, so, let's write these down. Oh, I guess I'm zoomed out all the way. All right, let's try like this. So when you take the Earth and project it onto from 3D onto 2D, I guess I should have said this. The three main types of projection that you could have are planar, conic, or cylindrical. Okay, and it's a caveat here. So there are projections that are hybrids of these types of projections, and what's, this is an oversimplification, because it turns out that literally there's an infinite number of projections that you can do, because these things are actually defined mathematically. They're a collection of mathematical equations that take latitude and longitude values and project them onto a flat surface, and so that they're mathematical functions, and there's no limit to the amount of functions you can write down. So thinking about these three main types of projections is helpful, because most projections can be categorized as being mostly this type or mostly this type, but I think it's important to understand that what's really going on here is this mathematical equations, and you can write mathematical equations to make a projection of this three-dimensional Earth onto a two-dimensional surface, and that surface could be anything. It could look like the petals of a flower, or I don't know, it could be wavy, it could be disconnected, it could be disjoint, the possibilities are endless. All right, but let's look at a couple examples of different projections, and I've programmed them up here. So what you're looking at here, this is the orthographic projection, this orthogonal projection onto a planar surface. It's like and I know it's rotating here, which makes it feel three-dimensional, but you're just looking at a two-dimensional thing, right? It's just flat on the screen. All right. If you guys, by the way, if you want to observe these yourself, the link is up here to this website. It's publicly available. Okay, let's change it. So the Mercator projection. So this is what you get when you take the Earth and project it onto a cylinder and then unravel that cylinder. Okay. So remember I said that all projections lead to distortions. All right, so let's go back here. Here it's obvious the distortions are at the edges. Things are not the shape that they should be. Look at this. I mean, here the distortion is near the poles. It's insane. Antarctica is not this big relative to, and also Africa is enormous, and it doesn't look as big as it actually is in this projection. Greenland, no, it's not this big. And the Mercator projection, so what's happening here is you can see that the Mercator projection creates a grid of latitude and longitude, and all the latitude lines are all the longitude lines are equally spaced, but the latitude lines get further and further apart as you get near the poles. And the reason this is happening is because, remember those longitude lines converge at the poles, and if you then take that and project that horizontally out onto the cylindrical surface, as you go to the poles, the amount of screen that you need to capture that projection just goes to infinity. So the Mercator projection doesn't actually capture the poles. It gets cut off at like 85 degrees north and south latitude, and everything above that isn't there. So you got to get use a different projection to capture the poles, because you can't, because you would need an infinite two-dimensional surface to capture it. Okay, so one of the advantages of the reason the Mercator projection was invented was because it's convenient for navigation. Let's go back here. Straight lines on a Mercator projection map are straight lines of bearing. So that's not saying the same thing as the shortest distance between 2 points, but it's the easiest way to navigate. Like if I wanted to go from California to Japan or California to Australia, I could use a Mercator projection to figure out my directional bearing, and then if I just follow that bearing on a compass, I would get there. And again, it's not the shortest path, because as you move across the Earth, your compass bearing is going to change. But if you stay on that constant bearing, you'll get there. So that's why they were invented. But the Mercator projections have serious distortions of area when you get near the poles. All right, let's look at another one. Are you guys enjoying this? Is this interesting to you guys? Have you ever thought about this before? I find this completely fascinating. It's it's just super cool to me. So here's a modified cylindrical projection. Here, this is the Plat Carré projection, and this is more like the modified Webb Mercator projection that Google uses. It's a cylindrical projection, but what it does here is it squishes the latitudes so that all the grids are the same size. You see that? But you still have these same distortions, and so now you have distortions in area, and you also have distortions in shape. Greenland doesn't look like this. Okay. I think I'll save the best for last. Let's look at here's the Albers equal area conic projection. So this is what you get, and notice the pole is missing. But this is a projection that you would get if your screen was conical in shape and then you unraveled it and laid it flat. And I said that this is let's do this. Do I have ArcGIS open? No. I'll show you some. I said this is the type of projection for a lot of maps you'd see on the wall of the United States. It's a good projection. If you look at the United States here, it pretty accurately reflects the shape of the United States, the area of the United States relative to other features, distances between points. It's a balance between all these different factors. It's a nice balanced projection. This one is the projection that National Geographic uses, and it's actually a modified planar projection. And all right, the best for last. Haha. So this is called the transverse Mercator projection. So this is like, in this picture here, the Mercator is based on a cylindrical surface like this, but this transverse Mercator turns the cylinder on its side. So here the cylinder makes contact with the equator, but if you turn it on this side, the cylinder will make contact with one of the lines of longitude. And so this might look like, well, this is crazy. There's super distortions at the edges, but what's really great about the Mercator, the transverse Mercator projection, is whatever line of longitude is right here in the center is, when it's straight up and down between the poles, there's very little distortion of area, of shape, of distance, or direction near that line of longitude at the middle of this projection. So I would say the universal transverse Mercator projection is my favorite map projection for making maps of things that are large scale, like if I was mapping my neighborhood, or I was mapping Shepherd University, or even mapping, Berkeley or Jefferson County. And you know who agrees? The USGS. This is what they use when they make their collection of maps they divided the United States up into grids that are about 7 degrees in size, longitude in size, and they use this projection. So it's, when you're looking at features that are, in large scale, high detail, it's a projection that's really good for preserving distances and areas and shapes. It doesn't introduce a lot of distortion, but only near that line of longitude where you're focused on. All right. Okay, so I spent a lot of time on that, more than I wanted to, or more than I was hoping to. I want to spend like 100 hours on map projections. It's super interesting, but let's change gears and let's do some work with ArcGIS Online, okay? And all right, going back to Chrome. Okay, so let me just show you some things. I just want to. So this is a map of the major geology layers in the United States, and we were working with it last Wednesday. But the textbook, one of the things it demonstrates is there's this huge repository of data online. So you can add layers to your map just by going to add and search for layers. And let's change this to ArcGIS Online. Okay, and let's search for the World Universal Transverse Mercator layer, and there it is. So I'll click that and I'll click Add to Map. And let's zoom out a little bit. So here you see the Universal Transverse Mercator divides the world up into this grid. And here in West Virginia, we're in the grid 17 or 18, depending where you are in Jefferson County, UTM zone 17 and 18. So if I were mapping, if I were making a map of Berkeley County or Jefferson County in West Virginia in ArcGIS, ArcGIS Pro, a good map projection to use would be the Universal Transverse Mercator projection for grid location 17 or 18. Okay, but that projection would not be good for a map of California. It would not be good for a map of Spain. Okay. I'll demonstrate that at some point in the coming days. All right, so you can always add layers using this feature. Okay, so let's go to, I want to save that. So chapter 1 in Understanding GIS also works with a map called, what's it called? It's called Pedestrian and Bicycle in Wilmington, Delaware. Okay, search for that map, and I want to search outside my organization. And I'm looking for the one by Michael Law. Here it is. And I'll open that in Map Viewer. And just to reiterate, everything that you guys all have accounts now for ArcGIS Online. So you can, anywhere you have a web browser, you can do work with ArcGIS Online. You don't need a Windows computer. You can do this on Mac. You just need a web browser. Okay. This chapter has you do some work with accidents. These are pedestrian and bike accidents. And one thing you can do, if you click on these features, what you're seeing is the row of the attribute table for that accident. And I mean there's a lot of information there. It's just overwhelming. It's not formatted very well. So one of the things that this chapter does is it shows you how you can change what these pop-ups look like. All right, and the way you do that is you go over here to the more options and do configure pop-up, and then configure attributes. Brings up this window where I'm going to turn everything off, and I think I'll just turn on a few things. So I'll turn, there's an attribute called pedestrian somewhere. Wow, so many. Where is it? There it is, pedestrian. So I'll turn that on. There's one called date of, hold on a second. Date of CR. I don't know what CR stands for. If I find it, I'll be happy. I saw date of CR. There it is. And then what you can do is, this is how this attribute will appear in the pop-up, but you can change the alias to something that's more meaningful. And I'll click OK. So now I only have these two dimensions of the attribute data that are going to appear in the pop-up. So now if I click over here, what the heck? Did I do it for? Let's try that again. Configure pop-up. Turn everything off, and where are you? Where are you? Where are you? Date. There it is. All right, and the other one was pedestrian. It was near the bottom here. Ooh. Okay. Okay. There we go. So now you're getting whether it's it's a much more useful pop-up window now. It's less overwhelming. Another thing that this chapter does is it shows you, well, let's change the symbology. Click this button right here, change the style for the symbols here, and the symbology is showing different symbols for accidents that were pedestrian accidents and accidents that were bicycle accidents. So you can click on these symbols, and they're using these symbols. You know, just different symbols for, and click OK, and done. And what did I do? It's weird, I'm having trouble getting things to stick. Okay. Done. There we go. Okay. So I changed my symbology. I'm not going to save this map. I got like 3 minutes here. So let me show you something else you can do. Let's say, you know, here I'm just showing accidents from 2014. But I can also turn on accidents from 2013. And let's say I wanted to do an analysis on all of this data at the same time. You know, one thing you could do is you could say, well, I have these two layers, and the only difference between those layers is that it's data from 2 different years, and like all the attributes are the same, you know, the tables are the same. What you can do is you can merge layers, okay? And let's do that. So if I go up here to analysis and do manage data, merge layers, and so here I'm going to take the accidents 2013 and I'm going to merge it with 14 and merge it with 13, and then I got to give this resulting layer a name, so that's fine, and I'm going to unclick this so that it works for all the data, not just the data that you can currently see on the map, the current map extent. And one thing is, this takes some credits. So this is going to take 0.155 credits. You guys, I'll click Run Analysis, see it's running right now. What does that mean? Whenever you run analysis on ArcGIS Online, it's using their server resources. And they, let's say, charge you for the server resources, but it's not like money. It's credits, and all of you have 100 credits right now, and if you use that up, we can probably get you some more. But you really need to do a lot of work to use that all up. All right, we come back here, and I turn off accidents 13, 14, and just have the merge of accidents 14 and 13. See, it's now they're on the same layer. So I could go here and I could do looking for pedestrian, A, B, C, D, E, F, G. I just passed it. There it is. So if I assign symbology based on whether there's a Y or an N in the pedestrian column, click OK, done. I can distinguish between, I'd have to change the pop-up again, bike accidents and pedestrian accidents. All right, so we'll call it there. We'll call it a day there. And you know, I'm going to keep showing you other stuff that you can do with ArcGIS Online and ArcGIS Pro. That's you know, a little bit above and beyond what's in your textbook. I'm going to try to, and think of these demonstrations as inspirational, you know, to just show you the world of possibilities, the types of stuff that you can do with a GIS, the types of analysis, and then that will teach you about the types of analysis that you can do with the GIS. All right, so good first week, team. Have a good weekend, and I will see you Monday.